August 14, 1945, 20,000 feet above Tokyo Bay, Captain Robert Morgan watched the city sprawl beneath his B-17 flying fortress like a vast mechanical puzzle waiting to be solved. For 3 years, American bomber crews had pounded Japanese industrial targets with varying degrees of success. Their bombing accuracy, measured across thousands of missions, averaged roughly 3% of bombs landing within 1,000 feet of the aim point. The statistics painted a sobering picture of aerial bombardment, where tonnage dropped rarely translated into strategic destruction. Morgan's bombardier, Lieutenant James Cartwright, hunched over a device that looked like it belonged in a university physics laboratory rather than a combat aircraft. The Norden Bombsight, a 50-pound mechanical computer bristling with gyroscopes, mirrors, and precision gears, promised to transform bombing from area saturation into surgical precision. The device could theoretically place a bomb within a 100-foot circle from 4 miles up, performance that seemed impossible given the variables of wind, altitude, and aircraft motion that plagued every bombing run. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. But beneath Morgan's aircraft, in a fortified bunker at the Mitsubishi Heavy Industries complex, Japanese engineers had no idea they were about to witness the culmination of America's most closely guarded bombing technology. A mechanical brain that could calculate trajectories faster than any human bombardier, compensating for factors that had made precision bombing nearly impossible since the first aircraft dropped explosives from open cockpits in 1914. The morning briefing at Tinian Airfield had carried the weight of 3 years of strategic bombing doctrine. Another mission deep into Japanese territory, another attempt to cripple the industrial infrastructure that kept enemy forces supplied with aircraft, ammunition, and fuel. Morgan stood before his crew in the Quonset hut, pointing to reconnaissance photographs that showed the Nakajima aircraft engine factory north of Tokyo. Intelligence estimated the facility produced 30% of Japan's fighter engines. Destroying it would ground hundreds of aircraft that might otherwise oppose the planned invasion of the home islands. Morgan's finger traced the route on the map. We'll approach from the east at 22,000 feet. Expect heavy flak over the target area. The factory complex measures approximately 800 feet by 400 feet. Our aim point is the main assembly building in the center of the compound. He paused, studying the faces of his crew. These men had flown dozens of missions together, had watched sister ships disappear into Japanese flak fields, had nursed damaged aircraft across hundreds of miles of Pacific Ocean. They understood the mathematics of strategic bombing better than any textbook could teach. Hitting a specific building from 4 miles up while the aircraft traveled at 180 miles per hour through turbulent air and hostile fire required solving ballistic equations that changed every fraction of a second. The reality of American bombing accuracy in the Pacific theater contradicted the confident predictions of pre-war aviation theorists. Military planners had assumed that modern bomb sites would enable precision strikes against critical infrastructure, crippling enemy war production through selective targeting. Instead, bombing operations devolved into area attacks where hundreds of aircraft saturated entire industrial districts, hoping that sheer volume would destroy the intended targets along with everything else in the vicinity. The statistics from the European bombing campaign illustrated the persistent challenges of aerial bombardment. American heavy bombers attacking German targets from high altitude achieved an average circular error of approximately 1,200 feet, meaning half of all bombs landed outside a circle with that radius centered on the aim point. Against targets smaller than half a mile across, this accuracy proved inadequate for reliable destruction. Strategic bombing required multiple missions against the same objective, exposing crews to repeated danger while giving enemy forces time to repair damage and strengthen defenses. Cartwright raised his hand from the bombardier's position mock-up they used for training. "Sir, what's the wind forecast for target altitude? Any word on thermal currents over the factory complex?" The question revealed the fundamental problem that had plagued bombardiers since altitude bombing became operational doctrine. Wind conditions at 20,000 feet bore little resemblance to surface weather, and thermal currents rising from industrial facilities created turbulence that made stable bombing runs nearly impossible. Traditional bomb sites required the bombardier to manually estimate wind drift and adjust his aim point accordingly, calculations that depended on experience, intuition, and considerable luck. The Norden Bombsight eliminated much of this guesswork through mechanical computation. Carl Norden, a Dutch engineer who had immigrated to America before the First World War, had spent 2 decades perfecting a device that could automatically compensate for wind, aircraft motion, and ballistic variables. The bombsight incorporated a stabilizing gyroscope that maintained its orientation regardless of aircraft movement, allowing the bombardier to track targets accurately, even through turbulence and evasive maneuvers. The device's computing mechanisms were revolutionary for their time. As the bombardier tracked his target through the Norden's telescope, the bombsight continuously calculated the aircraft's ground speed and drift angle by measuring how fast the target moved across the field of view. These measurements fed into a mechanical analog computer that solved the ballistic equations necessary to determine the precise moment when releasing the bomb would result in it striking the intended aim point. But the Norden's most remarkable feature was its autopilot integration. During the bombing run, the bombardier could actually fly the aircraft through the bombsight itself, making tiny corrections to the flight path that kept the crosshairs centered on the target. The system bypassed the pilot entirely for the critical minutes before bomb release, ensuring that human reflexes and judgment errors wouldn't compromise the precision that the mechanical calculations provided. Morgan had witnessed the Norden's capabilities during training exercises over the Salton Sea bombing range in California. Bombardiers using the device consistently placed practice bombs within 200 feet of the target from altitudes exceeding 20,000 feet, performance that seemed almost magical compared to the scatter patterns produced by earlier bomb sites. The implications were staggering. If such accuracy could be replicated in combat conditions, American bombers could strike specific buildings within industrial complexes, destroy individual bridges and railroad yards, and eliminate critical infrastructure without devastating entire cities. However, Morgan also recognized the challenges that combat operations imposed on precision bombing. The Salton Sea range offered ideal conditions: clear weather, no hostile fire, unlimited time to set up bombing runs. Japanese defenses would provide none of these luxuries. Anti-aircraft guns would force constant evasive maneuvers. Cloud cover might obscure targets until the last moment. Equipment malfunctions could disable the Norden's delicate mechanisms. The gap between training performance and combat effectiveness had destroyed many promising weapons systems throughout military history. The development of the Norden Bombsight had consumed enormous resources during a period when America struggled to modernize its military forces. Carl Norden's initial designs, dating to 1923, had shown promise but lacked the refinement necessary for operational deployment. The Navy had funded continued development throughout the 1920s and 30s, investing over $1 million in a program that many officers considered an expensive gamble on unproven technology. Norden's obsessive perfectionism drove the project's extended timeline. He insisted on manufacturing tolerances measured in 10,000ths of an inch, rejected components that didn't meet his exacting standards, and personally supervised the training of bombardiers who would operate his creation. The bombsight incorporated over 2,000 precision parts, many machined from exotic materials like aluminum, bronze, and stainless steel, to ensure stability under the extreme conditions of high-altitude flight. The strategic implications of precision bombing technology had become apparent to American military planners during the late 1930s. War in Europe demonstrated that modern industrial economies could absorb tremendous punishment through area bombing while maintaining military production. German factories dispersed operations across multiple facilities, concealed critical equipment in underground bunkers, and rapidly repaired damage from conventional air raids. Breaking this resilience required the ability to strike specific targets, bottlenecks in production that couldn't be easily replaced or relocated. American war planners identified several critical target categories where precision bombing could achieve strategic effects impossible through area attacks. Oil refineries, chemical plants, and precision machinery factories all contained equipment that was both essential to war production and difficult to replace. A single well-placed bomb could destroy catalytic crackers or specialized machine tools worth millions of dollars, crippling production for months. But achieving such precision from 4 miles up demanded technology that didn't exist when America entered World War II. The Norden Bombsight represented America's attempt to overcome the fundamental limitations of gravity-based weapons delivery. A bomb dropped from a moving aircraft followed a parabolic trajectory influenced by initial velocity, air resistance, wind, and gravity. Calculating this trajectory required solving differential equations that incorporated dozens of variables, many of which changed continuously during the bombing run. Human bombardiers using simple mechanical sights couldn't perform these calculations accurately enough to ensure hits against small targets. Norden's solution combined gyroscopic stabilization with analog computing in ways that pushed the boundaries of 1940s mechanical engineering. The sight's stabilization platform maintained its orientation using a gyroscope spinning at 12,000 revolutions per minute, fast enough to provide the rigidity needed for accurate targeting despite aircraft vibration and movement. This platform supported a telescope that gave the bombardier a magnified view of the target, allowing precise tracking even from extreme altitudes. The analog computer portion of the bombsight accepted inputs from the bombardier and sensors measuring aircraft motion, then continuously solved the ballistic equations needed to predict bomb impact points. The computer used a series of mechanical cams, gears, and differential mechanisms to perform calculations that would have required several minutes using slide rules and trigonometric tables. The system updated its solution 30 times per second, ensuring that the bomb release signal would be generated at precisely the correct instant, regardless of last-minute changes in aircraft speed or direction. Integration with the aircraft's autopilot system represented the final piece of the Norden's design philosophy. The bombsight generated steering commands that automatically corrected the aircraft's flight path, maintaining the precise heading and speed needed for accurate bombing. This eliminated the largest source of error in traditional bombing, the pilot's inability to fly a perfectly straight and level course, while simultaneously avoiding flak and maintaining formation position. The mission to the Nakajima factory proceeded exactly as Morgan had predicted during the briefing. The B-17 formation crossed the Japanese coast at 0800 hours, climbing to bombing altitude as they turned toward their target. Anti-aircraft fire began at 30 miles from the objective, black puffs of smoke erupting in patterns designed to force the bombers into evasive maneuvers that would compromise their bombing accuracy. But Morgan maintained course and altitude, trusting the Norden Bombsight to compensate for minor variations in flight path. Cartwright activated the device 10 minutes before the planned bomb release point, allowing its gyroscopes to stabilize and its computers to begin calculating ground speed and wind drift. The bombardier's eye pressed against the telescope's rubber eyepiece, watching as the factory complex gradually resolved from a dark smudge into distinct buildings and smokestacks. The view through the Norden's optics revealed details that would have been invisible to the naked eye from 20,000 feet. Cartwright could distinguish individual railroad cars in the factory's marshalling yard, identify specific buildings based on their roof configurations, and select precise aim points within the larger complex. The magnification that made such observations possible also introduced challenges. Every minor aircraft movement translated into dramatic shifts in the visual field, making target tracking difficult without the bombsight's stabilization systems. Cartwright centered his crosshairs on the main assembly building's roof, a rectangular structure approximately 200 feet long that intelligence photographs had identified as containing the critical engine production machinery. The Norden's tracking mechanisms automatically measured how fast the target moved across the field of view, data that fed into the ballistic computer's wind drift calculations. The bombardier made small adjustments to the aircraft's heading, using the bombsight's autopilot controls, tiny corrections that kept the crosshairs perfectly centered despite turbulence and the buffeting from nearby flak bursts. The final minute before bomb release required absolute concentration from both the bombardier and the mechanical systems supporting his efforts. The Norden continuously updated its solution as new data arrived from tracking sensors and motion detectors. Wind estimates refined themselves as the bombsight accumulated more measurements of target drift. The ballistic computer adjusted its release point calculation to account for the most recent measurements of ground speed and altitude. At precisely 0847 hours and 32 seconds, the Norden Bombsight triggered the automatic release mechanism that dropped 8 500-pound bombs from the B-17's internal bay. The weapons fell away cleanly, beginning their 4-mile descent toward the Nakajima factory complex. Each bomb followed a slightly different trajectory based on minor variations in aerodynamic characteristics and release conditions, but all remained within the dispersion pattern that the Norden's calculations had predicted. Cartwright watched through his telescope as the bombs plummeted toward their target, willing them to follow the trajectory his mechanical computer had calculated. The 43 seconds between release and impact seemed to stretch endlessly, filled with the uncertainty that accompanied every bombing mission, regardless of the sophistication of aiming equipment. The first bomb struck the factory's main assembly building 7 feet from Cartwright's aim point, penetrating the roof and detonating inside the structure, where it would cause maximum damage to machinery and structural supports. Subsequent bombs walked across the target area in a tight pattern that destroyed the northern third of the factory complex, exactly as the mission planners had intended. Secondary explosions erupted as stored fuel and ammunition ignited, sending towering columns of black smoke thousands of feet into the air. Morgan banked the B-17 away from the target, giving his crew a clear view of the destruction below. The bombing pattern showed none of the wide scatter that characterized attacks using conventional bomb sites. Instead, the impacts clustered within a 200-foot circle, precision that seemed impossible given the altitude, weather conditions, and hostile fire the aircraft had encountered during the run. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The post-mission analysis at Tinian revealed the strategic significance of what had occurred over the Nakajima factory. Reconnaissance photographs taken 48 hours after the raid showed that American bombs had destroyed approximately 60% of the facility's production capacity through direct hits on critical buildings. Previous raids against similar targets had required multiple missions and hundreds of bombs to achieve comparable damage, exposing crews to repeated danger while giving enemy forces time to implement defensive measures. The Norden Bombsight had delivered exactly what its designers had promised: the ability to place bombs precisely where they would cause maximum damage to enemy war production. The technology transformed strategic bombing from an expensive war of attrition into a surgical instrument capable of striking specific vulnerabilities in industrial infrastructure. The euphoria surrounding the Nakajima factory raid dissipated within weeks as subsequent missions revealed the sobering limitations of precision bombing technology. The Norden Bombsight, for all its mechanical sophistication, remained vulnerable to factors that no amount of engineering could overcome. Weather conditions over the Japanese home islands during the summer of 1945 created cloud cover that obscured targets on 60% of scheduled bombing missions. Without visual contact, the Norden's optical tracking systems became useless, reducing bombardiers to crude dead reckoning estimates that produced accuracy no better than pre-war bomb sites. Major William Patterson reviewed the bombing photographs from the previous week's missions at 20th Air Force Headquarters on Guam, each image telling the same frustrating story. Bombs scattered across wide areas surrounding their intended targets, industrial facilities, damaged but still operational, critical infrastructure surviving intact, while surrounding residential areas bore the brunt of missed strikes. The gap between the Norden's theoretical capabilities and its operational performance was growing wider with each mission over Japan. The technical challenges began with the bombsight's optical system. The Norden's telescope provided 20-power magnification, essential for identifying specific buildings from 20,000 feet, but this magnification transformed minor atmospheric distortions into serious targeting errors. Heat shimmer rising from industrial facilities during summer months created visual distortions that made precise aim point selection nearly impossible. Bombardiers reported watching their crosshairs waver and jump as thermal currents bent light in unpredictable patterns. Lieutenant Richard Hawkins, one of the most experienced bombardiers in the 5th Bombardment Group, documented these challenges in his mission reports with scientific precision. During a raid against the Kawasaki Steel Works on August 7th, he had achieved perfect tracking conditions for the first 8 minutes of his bombing run. The Norden's gyroscopes stabilized flawlessly. The autopilot maintained heading within half a degree, and wind drift calculations appeared accurate based on ground speed measurements. Then, at 3 minutes before bomb release, atmospheric conditions over the target changed dramatically. Rising heat from the steelworks blast furnaces created a thermal column that lifted the B-17 by 200 feet in less than 10 seconds. The sudden altitude change invalidated the Norden's ballistic calculations, which assumed constant altitude during the final approach. By the time the bombsight recalibrated for the new flight level, the aircraft had already passed the optimal release point. Hawkins' bombs fell 600 feet short of the target, destroying several warehouses but leaving the critical steel in production facilities untouched. The problem wasn't limited to thermal disturbances. Japanese anti-aircraft defenses had evolved specifically to counter American precision bombing tactics. Flak batteries no longer attempted to shoot down individual bombers, but instead created box barrages, dense concentrations of exploding shells that forced aircraft into evasive maneuvers during their bombing runs. The Norden Bombsight required straight and level flight for at least 3 minutes before bomb release to achieve its advertised accuracy. Japanese gunners exploited this vulnerability by concentrating their fire during the final approach to target, gambling that American pilots would prioritize crew survival over bombing precision. Captain Morgan faced this dilemma on August 21st during a mission against the Yokohama dockyards. His bombardier had established perfect tracking on the target. The Norden's computers were generating a solid firing solution, and bomb release was scheduled for 45 seconds in the future. Then a flak burst erupted 30 feet off the starboard wing, shrapnel tearing through the aircraft's horizontal stabilizer and puncturing the No. 3 fuel tank. Morgan's instincts as a pilot screamed at him to take evasive action, to drop altitude and turn away from the flak concentration that was clearly bracketing his aircraft. But breaking off the bombing run would waste the entire mission. His bombardier had only one chance to release the bombs with any hope of accuracy. Maintaining course meant exposing his crew to concentrated anti-aircraft fire for another 3/4 of a minute, an eternity when high explosive shells were detonating close enough to rock the aircraft. Morgan held his heading, trusting his bombardier and the Norden Bombsight to make the risk worthwhile. The bombs dropped precisely on schedule, following trajectories that the mechanical computer had calculated down to fractions of a second. 7 of the 8 weapons struck within the target area, destroying 2 dry docks and damaging a heavy cruiser under construction. But the flak had taken its toll. Morgan's B-17 struggled home on 3 engines, fuel streaming from multiple punctures and 2 crew members wounded by shrapnel. The mission was technically successful, but the human cost raised questions about whether precision bombing justified the risks that achieving such precision demanded. The strategic bombing campaign against Japan had originally been planned around the Norden Bombsight's theoretical capabilities. American war planners assumed that precision attacks could systematically dismantle Japanese war production by destroying specific bottlenecks, oil refineries, aircraft factories, and machine tool plants that couldn't be quickly replaced or dispersed. Intelligence analysts had compiled target lists that identified 23 critical industrial facilities whose destruction would cripple Japan's ability to continue fighting. Reality proved far more complex than the planning assumptions suggested. Japanese industry had already begun dispersing production to smaller facilities, underground workshops, and residential areas where precision bombing became impossible without massive civilian casualties. The aircraft engine factory that Morgan's squadron had struck so successfully in August represented an older generation of concentrated industrial targets. Newer production facilities were deliberately designed to resist precision attack by distributing critical operations across multiple locations. Major General Curtis LeMay, commanding the 20th Air Force's strategic bombing operations, confronted these limitations during a heated staff meeting at his Guam headquarters on August 28. His operations officers had presented bombing effectiveness data that contradicted 3 years of strategic doctrine. The Norden Bombsight, when employed under optimal conditions by experienced bombardiers, could achieve remarkable precision, but optimal conditions occurred on less than 30% of missions over Japan. Cloud cover, thermal disturbances, mechanical malfunctions, and combat damage combined to reduce the bombsight's effectiveness to levels barely superior to conventional aiming methods. LeMay had built his reputation on tactical innovation and willingness to challenge established doctrine. His analysis of the bombing data led him to a controversial conclusion. High-altitude precision bombing with the Norden sight was not achieving the strategic effects that pre-war theorists had predicted. Japanese industry continued functioning despite months of attacks that should have paralyzed war production. American bomber crews were dying to achieve precision that operational conditions made largely theoretical. The alternative approach that LeMay proposed violated every principle of precision bombing doctrine. Low-altitude area attacks using incendiary weapons against Japanese cities, deliberately targeting the dispersed industrial facilities and residential workshops that had proven immune to high-altitude precision strikes. The Norden Bombsight would become largely irrelevant in such operations, its sophisticated computing capabilities wasted on missions that simply saturated entire urban districts with fire. The debate that followed LeMay's proposal revealed fundamental disagreements about the nature of strategic bombing and America's moral obligations in warfare. Officers who had spent years mastering the Norden Bombsight argued that abandoning precision bombing represented a failure of will and imagination. The technology worked when properly employed. The solution was better training, improved weather forecasting, and more persistent attacks against specific targets until they were destroyed. Critics of precision bombing pointed to the casualty statistics that told a different story. American bomber losses over heavily defended, Japanese targets averaged 8% per mission, rates that could not be sustained indefinitely without exhausting available crews and aircraft. The elaborate training programs for Norden bombardiers consumed months of time and enormous resources to produce specialists whose skills proved marginally more effective than conventional bombing methods under actual combat conditions. Carl Norden himself remained convinced that operational failures reflected improper employment of his technology rather than fundamental limitations in the bombsight's design. He argued that bombardiers needed more training time, that aircraft commanders should show greater willingness to accept risks during bombing runs, and that mission planners should select targets more carefully based on weather forecasts and defensive capabilities. The bombsight could achieve its advertised precision, but only when the entire tactical system supporting it functioned flawlessly. The gap between Norden's engineering perspective and LeMay's operational reality reflected broader tensions within American military aviation. Engineers focused on technical performance under controlled conditions, measuring accuracy in feet and calculating probabilities based on ideal scenarios. Combat commanders dealt with chaos, mechanical failures, human exhaustion, and enemy actions specifically designed to prevent optimal weapon performance. The Norden Bombsight represented the apex of mechanical computing technology for its era, but it existed within a tactical environment that frequently denied it the conditions necessary for success. Lieutenant Cartwright experienced these frustrations firsthand during a mission against the Osaka Arsenal on September 2nd. His Norden Bombsight functioned perfectly throughout the approach to target. Gyroscopes stabilized, computers calculated wind drift accurately, autopilot integration maintained precise heading. Then, at 90 seconds before bomb release, the telescope's optical system fogged over due to rapid temperature changes as the aircraft descended through an altitude where condensation formed on cold glass surfaces. Cartwright frantically wiped the eyepiece with his glove, but moisture had condensed inside the sealed optical assembly where he couldn't reach it. His view of the target dissolved into a blur, punctuated by vague dark shapes that might have been buildings or might have been shadows on the ground. The Norden's mechanical brain continued calculating a firing solution based on tracking data that was now 45 seconds out of date. Cartwright had to make an instantaneous decision: abort the bombing run and circle for another attempt, or release the bombs based on educated guesses about where the target lay beneath the fog. He chose to release, gambling that his initial tracking had been accurate enough and that the ballistic computer's calculations remained valid. The bombs fell away, their trajectories determined by data that had been correct 90 seconds earlier, but might no longer reflect current conditions. Post-strike reconnaissance showed that 4 of the 8 bombs had struck within the arsenal complex, damaging several storage buildings, but missing the ammunition production facilities that were the mission's primary objective. The incident illustrated a fundamental challenge that no amount of engineering sophistication could overcome. Precision bombing required maintaining continuous target tracking from initial acquisition through bomb release, typically a span of 10 to 12 minutes. Any interruption in that tracking, whether from optical problems, mechanical failures, or combat damage, degraded the Norden's accuracy to levels approaching crude estimation. The bombsight's complexity became a liability when component failures cascaded through systems that depended on flawless integration to function effectively. Maintenance challenges compounded the operational difficulties. The Norden Bombsight contained over 2,000 precision parts that required regular calibration and adjustment. Forward-deployed squadrons lacked the specialized tools and trained technicians needed to properly maintain such complex equipment. Bombardiers learned to perform field repairs using improvised methods that horrified Carl Norden's engineers, but kept the bombsights operational under conditions where proper maintenance was impossible. Technical Sergeant Harold Mitchell, the senior bombsight technician for the 498th Bombardment Group, documented the maintenance crisis in reports that never reached higher headquarters. His unit had 32 Norden bombsights, of which typically 8 to 10 were fully operational at any given time. The remainder suffered from various malfunctions, ranging from minor calibration drift to complete gyroscope failures. Mitchell's maintenance logs showed that the average bombsight required 40 hours of specialized maintenance for every 10 hours of combat operation. The spare parts situation was equally grim. Norden's manufacturing specifications demanded components machined to tolerances that exceeded standard military production capabilities. Replacement gyroscopes took 6 weeks to arrive from the United States, assuming the requisition reached the right depot and received proper priority. Bombardiers flew missions with equipment they knew was degraded, hoping that partially functional Norden sights would provide better accuracy than reverting to backup aiming methods. The security restrictions surrounding the Norden bombsight created additional operational burdens that reduced its combat effectiveness. Military regulations classified the device as secret equipment that required special handling procedures. Bombardiers were forbidden from discussing the bombsight's operation with anyone lacking proper security clearances. Guards were posted on aircraft whenever Norden sights were installed. Combat missions included specific orders detailing procedures for destroying the bombsight if the aircraft was forced to land in enemy territory. These security measures, while understandable given the technology's strategic importance, interfered with the collaborative problem-solving that effective combat operations demanded. Pilots and bombardiers couldn't discuss optimal tactics for employing the Norden, because doing so might reveal classified information about its capabilities. Maintenance personnel operated under restrictions that prevented them from sharing solutions to common problems across different units. The obsessive secrecy that protected the bombsight's technical details also isolated the specialists who operated it from the broader community of expertise that might have helped overcome its limitations. Japanese intelligence eventually acquired detailed information about the Norden bombsight through multiple channels. A B-17 forced to land in neutral territory during 1943 provided access to an intact example. German technical intelligence shared information obtained from captured American aircraft. By 1945, Japanese military analysts understood the Norden's capabilities and limitations well enough to design countermeasures, specifically targeting the conditions it required for accurate operation. The most effective Japanese countermeasure proved to be the simplest. Smoke generators positioned around critical industrial targets created artificial cloud cover that blocked visual acquisition during bombing runs. The smoke dissipated too quickly to provide permanent concealment, but it lasted long enough to disrupt the continuous target tracking that the Norden demanded. American bombardiers found themselves staring at grey obscuration instead of industrial facilities, forced to estimate aim points based on where they remembered seeing the target before the smoke appeared. Combat experience gradually revealed that the Norden Bombsight's advertised accuracy, placing bombs within a 100-foot circle from 20,000 feet, represented a best-case scenario that operational conditions rarely permitted. Actual combat accuracy averaged closer to 600 feet circular error, better than conventional bomb sights, but far short of the surgical precision that pre-war doctrine had assumed. This gap between theoretical and actual performance had profound implications for strategic bombing effectiveness. The mathematics were unforgiving. A target measuring 200 feet across required bombs to land within 100 feet of the aim point to ensure destruction. With a 600-foot circular error, approximately 20% of bombs struck the intended target, while the remainder caused collateral damage to surrounding areas. Destroying a specific industrial facility required multiple missions to achieve the cumulative damage that precision doctrine suggested should result from a single strike. American bomber production had been scaled to support the precision bombing strategy that the Norden Bombsight supposedly enabled. Factories across the United States manufactured thousands of the devices at enormous cost, each one requiring specialized labor and exotic materials that could have supported other weapons programs. The investment made sense if precision bombing could achieve strategic effects impossible through conventional methods. But if operational accuracy remained marginally better than simpler aiming systems, the resources consumed by Norden production represented a massive misallocation of America's industrial capacity. The war's end on September 2, 1945, brought an unexpected reckoning for the men who had built their reputations on precision bombing doctrine. The Norden Bombsight, once hailed as America's secret weapon that would revolutionize aerial warfare, now faced scrutiny from analysts examining 3 years of combat data with the cold objectivity that peace permitted. The numbers told a story that contradicted the confident predictions of pre-war strategists and the mythology that had grown around Carl Norden's mechanical marvel. Major Patterson assembled the comprehensive bombing effectiveness study at Strategic Air Forces headquarters on Guam, compiling mission reports from every B-17 and B-29 squadron that had operated over Europe and the Pacific. The statistical analysis consumed weeks of painstaking work, cross-referencing bomb damage assessments with weather reports, defensive conditions, and equipment status logs. The conclusions challenged fundamental assumptions about precision bombing that had shaped American air doctrine for a decade. American heavy bombers equipped with Norden bombsights had achieved an average circular error of approximately 1,100 feet during combat operations over Japan. This accuracy represented a significant improvement over the 2,000-foot circular error typical of conventional and bombsights, but fell far short of the 100-foot precision that Norden had demonstrated under ideal testing conditions. More troubling, the data showed that bombing accuracy actually decreased as mission complexity increased. Heavily defended targets where precision mattered most were precisely the conditions where the Norden's performance degraded most severely. The cost-benefit analysis produced even more sobering conclusions. The United States had manufactured approximately 50,000 Norden bombsights during the war, at a total cost exceeding $15 million, equivalent to over $200 million in 1945 purchasing power. Each bombsight required 40 hours of specialized labor to produce, and another 60 hours of training time for bombardiers to achieve basic operational competency. The resources consumed by the Norden program could have manufactured over 3,000 additional heavy bombers or provided air crews with substantially more training time. Carl Norden's response to these assessments reflected the wounded pride of an engineer whose life's work faced criticism from military bureaucrats who lacked his technical sophistication. He argued that the bomb sight had performed exactly as designed, achieving its specified accuracy whenever properly employed by trained operators under suitable conditions. The operational failures reflected inadequate training, poor mission planning, and commanders' unwillingness to accept the tactical constraints that precision bombing required. His device was not flawed, the military simply hadn't used it correctly. The debate intensified when General LeMay published his after-action assessment of the strategic bombing campaign. LeMay's analysis drew a stark distinction between bombing effectiveness during the high-altitude precision phase of operations and the low-altitude incendiary campaigns that followed. The precision missions, despite their technological sophistication and careful targeting, had destroyed approximately 30% of Japan's designated strategic industrial capacity. The area attacks using incendiary weapons, crude by comparison but executed under conditions where defensive fire was most lethal, had eliminated over 60% of urban industrial facilities. The implications were devastating for precision bombing advocates. American air crews had suffered their highest casualty rates during missions that employed the most sophisticated bombing technology. The Norden Bombsight, rather than reducing the risks of strategic bombing through improved accuracy, had actually increased crew exposure by requiring prolonged straight and level flight during final approach to target. Japanese anti-aircraft gunners quickly learned to concentrate their fire during these vulnerable periods, achieving kill rates that made precision bombing missions significantly more dangerous than area attacks. Lieutenant Cartwright struggled to reconcile his combat experience with the broader strategic assessments emerging from post-war analysis. He had witnessed the Norden's capabilities firsthand, had achieved bombing accuracy that seemed impossible using conventional methods. Yet he also remembered the missions where optical failures, mechanical problems, or combat damage had reduced his sophisticated bomb sight to an expensive paperweight. The gap between the technology's potential and its operational reality haunted him as he reviewed his own mission reports with the benefit of hindsight. The Nakajima factory raid that had seemed so successful in August now appeared more ambiguous when examined against comprehensive bombing effectiveness data. The mission had destroyed 60% of the facility's productive capacity, an impressive achievement by any standard. But post-strike intelligence revealed that Japanese engineers had dispersed the remaining manufacturing operations to 17 smaller facilities within 2 weeks. The precision strike that should have eliminated aircraft engine production for months actually resulted in a decentralized industrial network that proved more resilient to subsequent bombing campaigns. This pattern repeated itself across Japan's industrial landscape. American precision bombing forced Japanese industry to adapt by dispersing operations, concealing critical equipment, and developing redundant production capabilities. The tactical success of individual Norden-guided strikes generated strategic adaptations that made subsequent precision bombing less effective. The technology's very success at destroying concentrated industrial targets accelerated the transition toward dispersed manufacturing that negated the advantages of precision attack. The human cost of precision bombing doctrine extended beyond American casualties to include hundreds of thousands of Japanese civilians killed during strategic bombing operations. The mythology surrounding the Norden bombsight had created expectations of surgical strikes that would minimize collateral damage while destroying military targets. Reality proved far messier. Bombs that missed their aim points by 600 feet regularly struck residential areas adjacent to industrial facilities. The cumulative effect of months of precision bombing campaigns was urban devastation that rivaled the destruction caused by deliberate area attacks. Post-war investigations revealed that Carl Norden had known about the gap between his bombsight's test performance and likely combat effectiveness since 1938. Internal company documents showed engineering assessments warning that atmospheric conditions, target obscuration, and defensive fire would significantly degrade bombing accuracy under operational conditions. Norden had suppressed these assessments, arguing that military customers needed to understand the device's theoretical capabilities rather than predicted combat performance. The ethical implications troubled many officers who had commanded precision bombing missions based on assumptions about the Norden's accuracy. Major General Haywood Hansell, who had helped develop American strategic bombing doctrine, later wrote that the gap between advertised and actual bombing precision represented a failure of intellectual honesty that had cost lives on both sides. Military planners had designed campaigns around capabilities that existed primarily in laboratory conditions, then blamed operational commanders when combat results failed to match theoretical predictions. The technical limitations that combat experience revealed sparked immediate post-war developments in bombing technology. The United States Army Air Forces initiated research programs exploring radar-guided bombing systems that wouldn't depend on visual target acquisition. Early experiments with radar bomb sites showed promise for attacking targets through cloud cover or at night, conditions where the Norden was completely useless. These systems introduced their own limitations, particularly regarding accuracy against small targets, but they addressed the weather dependency that had plagued optical bombing throughout the war. The advent of nuclear weapons fundamentally changed the calculus of bombing accuracy. The atomic bombs dropped on Hiroshima and Nagasaki required only crude aiming to achieve their strategic effects. A weapon with a destructive radius measured in miles didn't need the precision that conventional bombing doctrine demanded. The Norden Bombsight's obsessive focus on placing bombs within 100-foot circles became irrelevant when a single weapon could obliterate entire cities. Strategic Air Command, established in 1946 to manage America's nuclear deterrent, initially equipped its bomber force with Norden Bombsights pending development of more advanced aiming systems. But the operational requirements for nuclear weapons delivery bore little resemblance to the precision bombing missions that had justified the Norden's development. Bomber crews needed to reach heavily defended targets, survive long enough to release their weapons, and escape the blast effects. Putting the bomb within a few miles of the aim point was sufficient given nuclear yields measured in kilotons. The Korean War provided a final operational test of the Norden Bombsight under conditions that more closely resembled World War II strategic bombing. B-29 bombers attacking North Korean industrial targets achieved circular errors, averaging 800 feet, better than Pacific theater performance, but still far from the precision that doctrine required. More significantly, communist air defenses forced American bombers to conduct most missions at night or through cloud cover, where visual bombing was impossible. The Norden sights sat unused while radar-equipped bombardiers guided weapons toward targets they never actually saw. Carl Norden died in 1965, his reputation diminished by post-war assessments that questioned whether his bombsight had justified its enormous cost and the strategic doctrine built around its supposed capabilities. He never publicly acknowledged the gap between his device's theoretical performance and combat effectiveness, maintaining until his death that proper employment would have validated his designs. The engineering community remembered him as a brilliant innovator who had pushed mechanical computing to its practical limits, while military historians debated whether his perfectionism had produced a weapon system too sophisticated for the chaotic conditions of actual warfare. The thousands of bombardiers who had trained on the Norden Bombsight carried conflicting memories of the technology that had shaped their wartime service. Some remembered missions where the device had performed flawlessly, enabling precision strikes that seemed impossible using conventional methods. Others recalled the frustration of watching sophisticated mechanisms fail at critical moments, optical systems fogging over, gyroscopes tumbling out of alignment, autopilot integration malfunctioning during final approach to heavily defended targets. Lieutenant Cartwright's post-war civilian career as a commercial airline navigator gave him perspective on the Norden's legacy that pure military analysis couldn't provide. The navigation computers that guided airliners across oceans incorporated many of the gyroscopic stabilization principles that Norden had pioneered. The autopilot integration that commercial aircraft used for precision approaches to airports descended directly from the bombing automation that the Norden sight had introduced. The technology's strategic bombing applications had proven disappointing, but its fundamental innovations influenced civilian aviation for decades. The mythology surrounding the Norden bombsight persisted long after combat experience had revealed its limitations. Popular accounts of World War II strategic bombing continued, describing the device as a wonder weapon that had enabled surgical precision against enemy targets. The phrase pickle barrel accuracy, supposedly describing the Norden's ability to place bombs in pickle barrels from 20,000 feet, became enshrined in aviation folklore, despite having no basis in actual combat performance. The gap between myth and reality reflected broader American narratives about technological superiority and precision warfare that would influence military doctrine for generations. Modern precision-guided munitions achieved the bombing accuracy that the Norden bombsight had promised, but never delivered under combat conditions. Laser-guided bombs and GPS-directed weapons routinely struck within 10 feet of their aim points from similar altitudes, performance that would have seemed like science fiction to World War II bombardiers. These systems succeeded where the Norden failed by eliminating the human operator from the ballistic calculation loop entirely, replacing mechanical computation with electronics that could process targeting data thousands of times faster, while remaining immune to the atmospheric disturbances and combat stress that had degraded optical bombing accuracy. The strategic lessons from the Norden program extended far beyond bombing technology. Military organizations repeatedly invested enormous resources in sophisticated weapons systems based on theoretical performance that operational conditions prevented them from achieving. The pattern recurred with advanced fighter aircraft that proved too complex for forward deployment, electronic warfare systems that enemy forces quickly countered, and command and control networks that collapsed under the chaos of actual combat. The Norden bombsight stood as an early example of the gap between engineering excellence and battlefield effectiveness that would challenge military innovation throughout the 20th century. Captain Morgan's final assessment of his combat experience with the Norden bombsight balanced recognition of the technology's genuine capabilities against acknowledgement of its operational limitations. The device had enabled bombing accuracy that saved American lives by reducing the number of missions required against heavily defended targets. But it had also created expectations of precision that combat conditions rarely permitted, leading to strategic decisions based on capabilities that existed more in theory than practice. The technology was neither the wonder weapon that propaganda suggested, nor the expensive failure that post-war critics claimed. It was simply a sophisticated tool that performed brilliantly under ideal conditions and struggled under the chaos that characterized actual warfare. The Norden bombsight production lines shut down in 1945, ending a program that had consumed enormous resources and generated intense controversy about the relationship between technological sophistication and combat effectiveness. The devices themselves gradually disappeared from military service as radar-guided and computer-directed bombing systems rendered optical aiming obsolete. Museums preserved a few examples, their precision mechanisms frozen in time, mechanical artifacts from an era when gyroscopes and gears represented the cutting edge of military computing. The final irony of the Norden story emerged decades later, when declassified intelligence reports revealed that German and Japanese engineers had developed similar gyroscopic bombsights during the war, but had chosen not to deploy them operationally. Axis technical analysts had concluded that the tactical constraints precision bombing imposed, prolonged straight and level flight during final approach, vulnerability to weather conditions, extensive training requirements, outweighed the accuracy advantages such systems provided. They had chosen simpler, more robust bombing methods that sacrificed precision for operational flexibility. This revelation suggested that American investment in the Norden bombsight might have reflected institutional biases toward technological solutions rather than objective assessment of operational requirements. The device's sophistication appealed to American engineering culture's faith that complex problems yielded to sufficiently advanced technology. The possibility that simpler methods might prove more effective under combat conditions challenged assumptions about the relationship between technological superiority and military success that had shaped defense procurement for decades. Thank you for watching. For more detailed historical breakdowns, Check out the other videos on your screen now, and don't forget to subscribe.